What is up, y'all? It is Jenkins back with your midweek review, reminding you of everything that's due on my agenda, expected to be done this week. Even if you missed a day, even if you forgot to log on Monday or Tuesday, I'm here for you. This is what is due. First and foremost, you have that catalyst, the week 5 catalyst. That's over last week's material. We'll go over that. And then we have the week 5 quick check, our new material, and that is going to be over acceleration, and we're going to go over that. Last but not least, we have a little virtual lab at the very bottom of the agenda. I want you to complete that lab. Remember, all of these exercises stay open, unlimited retry. It's up to you to get them done. If you do not see me in person, I need to see you Thursday and Friday at 11 o'clock, depending on your period, 11 o'clock Thursday or Friday, A-Day or B-Day, so we can go over this in person, face-to-face. So let's start with what we did last week on this catalyst, right? Let's start with what we know. We talked at the very beginning of school about what it means to go fast, right? To have speed. And you guys found out that speed is just the distance that you go divided by the time it takes, right? And if I add a direction component to that, a vector, that becomes velocity, right? The displacement over time, right? Same thing. This one has direction, scalar, vector, just a little bit of review. Now, the magic comes when we start breaking this down, right? When we start graphing it. And these graphs are super important, right? You need to know how to read them. So just like Mr. Reyes taught you, we have our x-axis and our y-axis. Here's my x-axis. Here's my y-axis, right? These are variables, right? This graph shows you the relationship between two variables in real life. X is not just X, Y is not just Y. These mean something, right? On the x-axis, we have something. On the y-axis, we have something. Well, if it's a relationship between two things, speed is the relationship between two things. Distance and time, or displacement in time. So let's talk about that. Let's talk about something speed or velocity. On the x-axis, we're always going to have time, right? You want to think of this x-axis as like time marches on, right? Time, you can't stop it. Everyone's going to die. Time marches on. You understand? So time is going to be on the x-axis, y'all. Time is going to be on the x-axis. So what's going to be on the y-axis, right? Up and down? Well, the only variable left is distance. So check me out. My distance is going to go on the y, right? So my distance. And I'm going to put my units, right? So I'm going to go with meters and seconds, right? Meters and seconds, right? Look at this. Look at this mirrored. Distance over time, right? Distance over time. Meters per second, which is the unit of speed and velocity. Meters per second. Meters per second. This over this. Let's watch. So what if I were to create a scenario where after every second, let's say I started at the origin, home, 0, like where I'm standing, and in 1 second, I walked 1 meter. And then the other second, I walked another meter. And then the other second, I walked another meter. You get me? Let's graph it. After 1 second, I walked a meter. After another second, I advanced another meter. After another second, I advanced another meter. And after another second, I advanced another meter, right? How do you read this, right? So as time goes on, for every additional second, how further did I get? How much further did I get away from the origin, 0, 0? Well, you should see that I get one more away, right? So I can make a line. I can graph that line. Now, what does it tell me? What about this line tells me what's going on here, the relationship between these? Well, how do you analyze a line? Well, let's look at the slope. Remember the slope? The slope is what? Rise over run, right? So we have rise over run. Rise over run. 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 Rise over run. So what is the rise of this line over the run of this line? Well, if I go up 1 and go over 1, right? Up 1, over 1. Up 1, over 1. Up 1, over 1, right? Up 1 and over 1 is rise over run, right? So look at rise. What does it mean to rise on this graph? Look at my variable. I get distance. I go 1 meter. My distance is rising. What am I running? My time. My time is my run. So if rise over run is distance over time, right? What does that mean? What is distance over time? It is here. It is the speed. It is the velocity. It is the speed. So the speed is distance over time. The same thing as rise over run. And rise over run describes the slope. Y'all follow it with me. The speed is distance over time, which is rise over run. It's the same thing as the slope. The slope is the speed. There we go. The slope of the line is the speed of the line. And y'all know this is true because if you're in person doing my outside running activity, right? Rip to Carlos Gregorio and Monty. They fell down and hurt themselves trying to win this race. Crazy, y'all. So y'all know that as time goes on, right, and distance goes up, you can have different slopes, right? So you should know by now what slope is the fastest? A, B, C. Which one is the fastest? You should see that, yes, it is A, right? You go a further distance in the least amount of time, right? If these are seconds, look how far you went in only 1 second. A is clearly faster. So this right here shows you the relationship between distance and time, D over T, right? So that's our speed. That's also our velocity, displacement over time. Same thing, but with direction. Now let's go over a couple more things. One, what if I cheated, right? We have that foot race, right? And let's say this is a Monty running so fast, right? Well, what if I cheated and I started, if this is where a Monty started at 0, 0, and this is distance and this is time, what if I got a head start? I would start right here, right? A head start. That's my intercept. So what if I got a head start and boom, he would catch up to me at around 1, 2, 3, 4 seconds. At 4 seconds, we would be at the same place, even though I got a head start because he's faster. This right here represents your head start, where you're starting from in relation to the origin, 0, 0. Monty started here, I started here. As time goes on, I'm running slow, he's running fast. He catches up to me right here and overtakes me, right? He wins. He's going to win this race as time goes on. So you need to know that as well. What does a starting point on the graph mean? Now, let's talk about something else. Y'all, nobody just walks at a constant speed, right? So what a constant speed means is this. So if I've got, again, you got to learn these graphs. We got X and we've got, that's going to equal time, remember? And I've got Y, and that's going to equal distance in meters and seconds, meters per second. I know what's happening here. After 1 second, 1. After 2 seconds, 2. After 3 seconds, 3. This is what we call constant speed. Do you know why it's constant? You can probably guess. It doesn't change, right? It's just walking like this. It's just going like this. It's not speeding up. It's not slowing down. Hardly anything works like that, y'all. Things happen, right? Forces act on things that speed them up or slow them down, right? So what would that look like? What would that look like? Let's brainstorm it. So if I have that same graph, and here's slow, and here's medium, and here's fast, right? How do I get from here all the way up to there? Could I change, right? Is there a way for me to change my slope, right? So if I'm going this way, how do I change to that slope? Well, I got to bend up. Now, how to change to that slope? Well, I got to bend up. And then all of a sudden, I have this cool curved line. And that shows me my velocity is increasing, right? So if my velocity is increasing, velocity increases, what do we call that? A velocity increase. Y'all, it's the little pedal next to the brake pedal, right? And it's called the accelerator because this is called acceleration. It's called acceleration, right? Now, what happens if the opposite is true, right? What if I slow down? What if I slow down? Let's look at that. Let's look at that. So what if I have a graph, right? And I'm up here, right? So how do I get from here down to a slower speed, right? A lesser slope, a less steep slope. Well, I'm going fast. Now I'm going to, see that curve? See that curve? That curve right there is also acceleration, except in the other way. So if this is accelerating and going faster, guess what this is? Accelerated and going slower, right? So if this is acceleration, guess what this is called? This one is called This one is called deceleration. Deceleration. Acceleration, deceleration, right? And this, of course, going back to it, is the constant speed. That would be constant speed. Constant speed. Constant speed. You need to know these graphs, all right? You need to know these graphs. Not only do you need to know the graphs, however, I need you to know the equations. So, let's do it. We've got speed slash velocity, distance over time, or displacement over time. These are the same, y'all. The same, except this has direction to it. We need to think about those directions, right? So we've got these, but what happens when I accelerate? Well, what changes when I accelerate? The velocity changes. My speed changes. So my velocity is going to change when I accelerate. So my acceleration is going to equal to, right? I'm going to start at one velocity, and I'm going to end up at another velocity. I have velocity 1, velocity 2. Now we're going to call those something. V sub f and V sub I. This is the final velocity. See that f? And this is the initial velocity. See that I? So what we're going to do here is we're going to take those and we're going to put these in this equation. V sub f minus V sub I over the change in time. Now this looks crazy. It's actually not. It's very simple. Check me out. So I've got two velocities. One's my final, one's my initial. All right, so what this is telling me is that it's going to change. Where I ended up and where I started, the difference between those is how much I change. And the acceleration depends on how much time it takes me to do that, right? So delta means change. So I could also write this. Acceleration is equal to the change in velocity over the change in time. How much did velocity change compared to how much time changed? That is the new equation I want you to work off of. That right there is so important. Let's do it. So I'm going to rewrite that equation here. Acceleration is equal to delta V, change in velocity, over delta T, right? So let me give you a scenario, right? So what if I started at 2 meters a second, right? So I'm going at a constant 2 meters a second. And then I picked up and I started running faster, right? I started running faster, and then that's 6 meters a second, right? Guess what? I started at 2 meters a second. Now I'm going faster. I'm accelerating to 6 meters a second. And it takes me, how long is it going to take me? 2 seconds to do that. So after 2 seconds, boom, I hit the jets, and now I'm going 6 meters a second. My question is, how much was my acceleration? What was the magnitude and the direction of my acceleration? Let's do it. How much did velocity change? Final minus initial. All right, let's do that. What is my final velocity? Is it 2 or is it 6? Well, final velocity is where I ended up with. So I've got 6. 6 meters per second minus 2 meters per second, where I started. Final minus initial. Do you see how this is the change in velocity? It changed from 2 to 6. So the difference between them is going to be 4. What is the change in time? How much time went by? 0, 1, 2 seconds. 2 seconds, right? So that's 6 minus 2 is 4 divided by 2. What is 4 divided by 2? It's 2. What are the units? Now let's be clear. Velocity is measured in meters per second. So this is 4 meters per second in 2 seconds. I have meters per second. Meters per second every second, which means that if I start here, after every second, I'm going to increase by 2 meters per second in my speed, in my velocity. 0 meters per second, 2 meters per second, 4 meters per second, 6 meters per second. I almost said something stupid. 8 meters per second. How much is it getting bigger by? By 2 meters per second every second. This is what we also called meters per second squared. If you ever see that meters per second squared, that's what meters per second means. Every single second, you're increasing your speed by 2 meters per second. That is acceleration. You get me? Let's go. How about, what if, and I'm going to write my equation here. Notice I'm always writing my equation, delta V over delta T, changing velocity, changing time. Let's say I started at 10 meters per second. Someone jumps out in front of me, and I slow down to 5 meters per second, right? And it takes me, let's say it takes me 2 seconds. 2 seconds to do so, right? So let me input. How much did the velocity change, final minus initial? You might say 5. You might say 5. You would be wrong, right? That's the magnitude. But this is a vector. What direction is it accelerating? Is it accelerating in the direction of motion or the opposite direction? You should see that this is slowing down. So if I do final, right? This is my final, minus my initial, it's 5 minus 10. 5 minus 10. Final minus initial. Then it becomes clear what these signs are all about. Y'all, negative doesn't mean underneath or less than or in the shadow realm. It means it's in the opposite direction. That's it, right? It's just as real. It's in the opposite direction. So 5 minus 10 over the time, 2. Now we can easily do that. 5 minus 10 is negative 5. You know what I'm saying? Negative 5 meters per second over time of 2 seconds, right? Y'all, negative divided by a positive, going to be a negative. You can see that 5 divided by 2, you should know that's 2.5. Negative 2.5 meters per second every single second, or as I like to say, and the majority of us like to say, meters per second squared. Negative 2.5. Why is it negative? Slowing down. The velocity is changing in the opposite direction, my guys and girls. Now, let's freshen up. Let's freshen this up. Check this out. If I have a graph, right, that shows you distance and time, distance over time. Velocity is distance over time, right? V is equal to d over t. This is a graph of d over t, distance over time, meters over seconds, distance over time, meters per second. Now, what does a graph of constant velocity freaking look like? Right here, constant velocity. What does a graph of acceleration look like? If I'm starting slow and go fast, I'm curving up. I start slow and go fast. That's acceleration, right? This is constant. Let me introduce you to another graph, however. This is on your quick check. What if instead of looking at these axes and saying, okay, distance versus time, right, in seconds, time, let me do velocity versus time, right, in meters per second. You should already, your fireworks should already be going off and saying meters per second over seconds, meters per second squared, velocity over time. What equation is this? If you said that acceleration is equal to delta V over delta T, that's what this shows. Bro, that's what this graph is. So this is what I'm trying to teach you, y'all. Don't look at these lines and try to understand what's going on. Look at the axes, and that will tell the story. As time goes on, what's happening to this axis? Why? The velocity is changing. It could go up, it could go down. Well, if I have changing velocity over changing time, what does that tell me? Acceleration. The slope of this line is velocity. The slope of this line is going to be acceleration. Now let's look at it. Take this one, constant velocity. Constant velocity. This is distance versus time. I'm getting a constant distance out of time. What about this over here? How would I say meters, my velocity over time? How would that look? Let's say I was going 2 meters per second, right? 2 meters per second. Well, look, meters per second is right here. There's 1 meter a second, there's 2 meters a second, there's 3 meters a second. So how would I show going a constant 2 meters a second, right? Velocity does not change. Well, if it doesn't change, it can't go up and it can't go down. It's got to go flat. That is constant velocity on this graph. Here, this is constant velocity on a meters per second distance versus time graph. But on a meters per second squared on a velocity versus time graph, that's constant. Do you see it? You have to read these axes correctly, right? You have to read them correctly. This right here is velocity compared to time. Is the velocity changing? No. But does that mean it's not moving? Absolutely not. It is moving. It's moving at 2 meters per second. That's 2 meters per second. This is 2 meters per second. These are the same thing. These green lines are the same thing on two different graphs. Now, let's go further. Let's go a little bit further. What would acceleration look like on this graph? Well, what is acceleration, right? Here, right, we see that the slope of the line is changing, bending upward, but that's distance versus time. In velocity versus time, how would velocity change, right? It would go from 1 meter a second to 2 meters a second to 3 meters a second to 4 meters a second to 5 meters a second to 6 meters a second. That looks like this. That's right, y'all. This is acceleration on this graph, a straight line. That's confusing, right? A diagonal line, straight, right, is constant velocity on this. A curved line is acceleration. But when I swap it and I make it velocity versus time, now the straight line is constant velocity and the diagonal line is acceleration. Wacky, right? Wacky stuff. This is how you read graphs, right? As time goes on, my velocity is increasing. As time goes on, my velocity is increasing. It's changing. Come on, y'all. That's acceleration. That's acceleration, right? As time goes on, velocity is increasing. Look at this one. As time goes on, my distance is increasing constantly or accelerated. These are the same thing. I've got my position versus time graph, my distance versus time graph, and my velocity versus time graph. You have to know both of these, ladies and gentlemen. This is on your quick check. Make sure you do it. I want to tease this one too. There is another equation. What if I am saying, okay, I changed my speed from 2 meters a second to 10 meters a second, but I couldn't time it. I didn't know how much time it took, but I know the distance or the displacement. I got a formula for that too, right? That would be my final velocity minus my initial velocity squared, don't freak out, over 2 times the displacement, so delta D. This right here, coming up at you soon, real soon. Learn how to use these equations, y'all. Learn how to use these equations. Acceleration, my final velocity minus my initial velocity, divided by time, change in time. This is the same thing as saying delta V over delta T. Delta meaning change in, change in. And again, y'all, that is velocity over time, changing my velocity. What if I decrease? What if I decelerated, right? That's changing my velocity. My velocity is going down. This is acceleration. Acceleration, deceleration. You know what I'm saying? This right here is a velocity versus time graph. Very different from the distance versus time graph, just like we showed before. This right here, constant velocity, acceleration. Let's go. Read these graphs correctly. Practice them. I'm here for you. Let me know if you need anything. Get my Catalyst done and get my quick check done. Love you guys. See you next week if you're Monday and Tuesday face-to-face. See you Thursday and Friday if you're on my Zoom call, my virtual Zoom, 11 o'clock. I'll see you there. Peace out.